and she basically wanted every single book by leg. So she had the list. But I asked her so much. She's like, I want this picture book, please give it to me.
So she got the list?
No, yeah. So she actually got that book I have, but then she gave it to me.
You're coming today, right?
Two.
Thing?
Still going today?
Yeah.
Yes.
But the problem is it's leftover stuff.
Yeah, all the stuff's good, all the good stuff's gone.
You should have seen this guy. Quick hands.
Alright, good morning everyone. So this is the last lecture, and as I said, we are not going to cover new material. I did want to make some announcements. So, well, first of all, something that probably worries you a lot and should worry you a lot because it's 50% of the mark. The final, I still don't know what will be the format of the final. So I asked the instructor on Tuesday, he didn't reply to me yet. So we will have to coordinate somehow because we have two sections and we cover slightly different material. So most likely the two finals will be slightly different, but also very, very similar, larger sections, something like this. Most likely it will cover kind of all the material from the beginning to the very end. I don't think there is, maybe just a little bit more way to game theory compared to kind of all other material. We only devoted a week and a half to game theory, probably will take a little bit more than is proportional on the final exam. But otherwise I have no real information. So please check our website for new updates. I will try to post exactly what material will be covered on the final, exactly how many questions, and well, I don't think that I will post kind of mock final, but at least I will send a link to what kind of problems from the past finals you should look at. And well, in general, you should look, of course, at all the problems from the past finals, except maybe, well, I'll talk about what material from previous years we did not include in our course and what new material we did cover in our course, which is not represented in past finals. So we'll talk about this. Another thing, yeah.
If you're not going to post a mock final, can you post some solutions to the past exams?
So I wasn't planning to, but if somebody can come up with solutions to, I don't know, the whole past exam or some questions, I am willing to take them and scan it and post on my website. I don't want to write them down. I mean, I am willing to actually check them, but not write them down. So it's up to you to coordinate. If you are solving some final anyway, and you are writing down your own solution, which is a very good idea to actually sit down and write it down. And you want it to be kind of checked, then maybe it's a good idea to actually give it to me and then check it and scan it and post it. So another thing, one student asked me about kind of we had 4 homeworks. They will be represented equally. Like we had a first homework was out of 20, second one was out of 24, third one was out of 7.5 or something like this. So they will be rescaled so that they will have equal weight. And then I planned for more homeworks, but now we have only 4. And one student asked me that kind of he missed one of the homeworks, and now he feels that too much of his grade depends on it. So I allowed him to submit his homework for half the credit. And well, to be fair, I will allow it for everyone. So if you haven't submitted all the past homeworks, you have a week from now to resubmit. Well, not to resubmit, but just to submit the past homework and to get half the credit for it. So I'll write this announcement down. let's see, 11 a.m. or 50%. So I think it's at least somewhat fair. I mean, I gave 100% of the credit for usual homeworks, 80% of the credit for slightly late homeworks, and now we have this option. So I hope it is. If you feel that you kind of missed one of the homeworks and you didn't deserve to get a 0, then try to use this option. What else? Yeah.
Will you have office hours before the finals?
So typically in my office, kind of every day from around 11 until 6, 7, sometimes 9, sometimes later. So you can just, pop in and knock on my door and ask me. Also, you can send me an email if you want. I mean, if you don't want to travel, you can call me to the same time that I'm not there and I can speak. So send me an email and arrange something, but I will not hold regular office hours. Today I will hold an office hour, but I will have to go at 2. So maybe it's not correct. Maybe today office hour. So I can't stay after 2 p.m. today. Yes, maybe any other questions, comments? Yeah.
Are we gonna get homework for that?
Oh, yes, sorry, I do have it. Maybe I should just grab it. Just wait 2 minutes. I'll be there. Sorry. Which classes?
So, interesting. It's called introduction to the Can you hold on?
Yeah, I'll definitely take a second. What time is it start?
At 12.
12.
And yesterday I got the 12:03, and there was already the 25.
Why don't you say this?
I was doing
So it's being passed around, it will get to you.
And I suppose you have leftover midterms too.
I don't have them here, but I do have them in my office. So, any other questions, comments? So I wanted I wanted just to kind of review the main topics that we covered in the course, just maybe kind of say the names and say what kind of problems would appear on the final related to these topics. So as I said, we did not discuss with the other instructor what kind of problems we will actually give to you. So first I'll say something about stuff that I don't know. In past exams, there have been some proof questions and some yes-no type questions. I have no idea whether we will have any of those. I mean, I will be pushing against proofs. I don't mind
outcome proofs in this
Hmm?
class. We get outcome proofs in this class.
Yes, so that's the thing. We kind of did have explanations and proofs in basic. I mean, when we talked about the theory, we did not emphasize kind of proper writing of the proof. So I will be pushing against this. with these kind of questions, yes, no questions, maybe it's a good idea actually to include something like this. It might be kind of a question. Suppose that the decision variable in the primal problem are not all non-zero, does it mean that the shadow prices are all zero? Something kind of, which sounds like complementary slackness, and you have to understand, is it actually complementary slackness or not quite? So something kind of, to check whether you actually understand and remember the proper text that we discussed. So maybe yes, but once again, I haven't discussed this with the instructor, so I can't promise. Otherwise, well, let's start talking about the most common kind of questions. So, NLP problem. And depending on the instructions, it could be just about the usual simplex method. Could be about one iteration of the simplex method, several of them, maybe several degenerate iterations. Could be some variations of this. Could be about this simplex method. So maybe the initial solution is not clear. You have to find at least one feasible solution. Maybe it could be about find all solutions. So some questions might have infinitely many solutions. You might be required to find all of them. If I do include such a question, I will explicitly say find all the solutions, or if it is about just making an iteration of the simplex method, I will say either perform one iteration or find at least one optimal solution. So I will try to be as clear as possible about this. Would be also show unbounded boundaries or divisibility. So some problems are unbounded or divisible, and you should know how to show this. Usually using the simplex method. So sometimes the problem is small enough that you can just guess any combination of the constraints which gives rise to some stupid constraint like -1 is greater than 0, and then you know that the problem is infeasible. So you should know such things. So that's let's say the most straightforward kind of questions. Then we have the topic of duality, which is actually a large topic. We devoted lots of time to it, and it's important. We've seen that it's important also in applications to game theory. So you should expect to get at least one or several questions in duality. And those could include simple questions like state dual problem, use control, check optimality, or proposed solution, find the solution of the dual, given the solution for the primal. So these kind of questions, you are given a solution to the primal. One question, check whether it's actually optimal. For this, you should remember that you first check feasibility, then you, using complementary slackness, you find the proposed dual solution, and then you check dual feasibility, whether dual constraints are satisfied. If both are satisfied, then you know that you found the optimal solution. For this one, well, it's even simpler. You have a solution which is promised to be the optimal solution. Just find the dual one using the complementary slackness. Another thing, we should remember the last row coefficients in the final dictionary. Are minus the dual variables. So you should know how to, given a dictionary, how to find, given the final dictionary of linear programming problem, how to, where to look for the shadow prices, the reduced costs. They are, well, with a negative sign, they are just the coefficients in the last row. So you should know this connection. Another thing is, well, you should know the words shadow prices and reduced costs. You should know the words, you should know what they mean, you should know kind of what implications some resource having a certain shadow price has on kind of sensitivity on the problems to increase the amount of resource by a little bit, how much will the profit grow. So you should know these kind of things. And you should know what kind of notions are known to each other. So duality of the following things. Let's say unbounded and indivisible. Variable and equality constraint. Another thing, decision variable. And select variable. So you should know that somehow, well, unbounded primal corresponds to invisible dual and vice versa. You should know that free variable in the primal corresponds to equality constraint in the dual and vice versa. We talked about this last lecture. You should know that, well, decision variables in the primal correspond to the select variables in the dual. Well, not exactly, not in the sense that they are equal, of course, but in the sense that the dual constraints the select variables for the constraint, which is about the coefficients of some given decision variable, so this kind of connection. Okay, so that's about duality. So if you have any questions, I mean, if you want me to remind what I mean by something, just ask me.
We do have a few variables in the primal. How would that look like in the dual?
So a free variable in the primal, it means that it could be positive or negative. It means that the corresponding constraint in the dual will not be an inequality constraint, it will be equality constraint.
Okay.
So that's what we discussed last class. Was more or less the last thing that we discussed in the course. So if you have, so typically you have the primal problem. It has all the inequalities are actual inequalities, and all the variables are positive. That's what usually happens. What it leads to is for each variable you can construct a constraint which kind of something times x1, something times x1, and so on. And then you construct the constraint this something times y1 plus this something times y2 plus and so on is equal to the coefficient of x1 is greater or equal than the coefficient of x1 in this problem. So if x1 is not positive, it can be free variable, then instead of inequality here for the dual, we will have this equality. So a free variable will give rise to an equality constraint. And vice versa. If here you have not all of those things are inequalities. If some constraint is an equality, then the multiplier, the thing by which you multiply, doesn't have to be positive. It will be positive or negative. So equality constraint is right between dual variables. Alright, then we have the revised simplex algorithm. Typical questions here, well, given a basis, find the next given and entering variables. So instead of giving you a problem to solve, I will give you a problem, give you a basis for some dictionary, so for some step of the simplex algorithm, just ask you what will be the next step, which variable will leave, which variable will enter, like we had in the midterm. So I will not require you to remember how to find an inverse of 3 by 3 matrix, 2 by 2 matrix, so you remember. I mean, it's not that 3 by 3 is hard, it's just 3 by 3 is kind of prone to arithmetical errors, and I don't want to punish it for just arithmetical errors. I will check whether you understand the material or just whether you know how to and subtract. Okay, so also shadow prices, values of decision variables. So maybe the problem is already solved for you. I mean, you know what is the basis and optimal solution. The question is, what are the shadow prices? What are the values of the decision variables? And for this, so shadow prices, it's about this kind of thing. It's the last row in the final dictionary. The values of the decision variables are the right-hand side values in the final dictionary, so you should know these formulas, D inverse D and CM minus CD inverse N. So you should know these formulas. In some of the past exams, the formulas were given to you. I don't think that we'll give you the formulas, you should just remember them or derive them very quickly. Well, of course, perform several steps. Simplex algorithm. So for this, if it's not just one step like here, you should also remember how to update the inverse, and you should remember this trick that we talked about, that you don't have to recompute the inverse from scratch. You can just do the pivoting. So you should remember this trick as well. And so something that did appear in past exams, but we won't have it. It's about eta factorizations. So we will not have this. If you see in the past exam something about eta matrices, just don't try to solve this. It's basically no different than what we did with updating the inverse using this pivoting operation. It's formulated in slightly fancier language, which is a little bit more convenient for implementing it in a computer, but we didn't really talk about efficient ways of implementing this, so we just know how to update the inverse using the pivoting. So we use a slightly different approach here. Then we have sensitivity analysis. Here, you should know when to use the dual simplex algorithm. And usual simplex algorithm. For reoptimization. So you might be given some problem, given the optimal solution for that problem, and then some variation of this problem. One of the numbers changed, one of the numbers becomes a parameter, one of the, well, several of the numbers have changed, new constraint is being added, or a new variable is being added, and the question is what is the new optimal solution? So you should know how to find the new final dictionary, and whether to find the actual new solution, you should perform the dual simplex method, the usual simplex method. So you should be familiar with these things. Another kind of question is ranges, where a given basis is optimal and feasible. So, like the output of sensitivity analysis from window, it tells you kind of how much you can change the right hand side in such and such line, so that the given basis is still optimal. So you should know how to do this. Same about coefficients of in the objective function. You should know how much they can change before a different variable will enter a basis. Well, and of course, you should know how to handle adding a constraint, a new constraint or a new variable. So change coefficients in the right hand side, the objective function. And we almost never talked about the matrix or the matrix. So when the change in coefficients in the right hand side or in the objective function, we know that, well, after finding the updated final table, we will be able to use either the dual simplex method or usual simplex method. For changing the actual matrix of coefficients in the problem, well, we know that it might lead to a new dictionary which is neither feasible nor optimal, and then we don't have, we didn't discuss a way to deal with such a problem. So if there is a change in the matrix, you should be sure, well, I promise that it will lead to either an infeasible solution which is optimal or feasible solution which is non-optimal. So we will not have kind of questions which are not about the material that we cover. So that's about sensitivity analysis.
So we'll either have optimal and feasible or infeasible but optimal.
So I'm saying that we have one situation which we didn't learn how to handle, when the new dictionary is neither feasible nor optimal. And I promise that such a situation will not appear on the file. Well, here also kind of parametric programming. So if the changes in the form will change some variables to some expressions using a variable. You should know how to handle such a situation. We will discuss an example of this because somebody asked me to actually go over an example once again. So we will. And we have just two more major topics. One of them is Lido. And for Lido, well, we don't have to, we don't have pagination, we will give you something similar to what happened on the midterm. Here's the reader output, interpret such and such things. So just questions of the type analyze, Lido output. And well, finally, the topic didn't cover either in homeworks nor in the midterms, so you should expect that it will actually appear on the final of this kind of somewhat large weight, I don't know, 20%, 25%, something like this. In theory, so for game theory, I will try to post some practice problems about game theory because, well, as I said, we didn't have any homework about it, we didn't have any midterm about it, so I will post some practice problems. So for game theory, the questions would define the optimal strategy. So this might involve, well, eliminating dominating strategies. So typically you want to eliminate first as many strategies as you can, and only then to formulate a linear programming problem, solve it, and interpret the solution as the probabilities which should be assigned to the strategies. So such kind of problem. Another kind of problem, given the optimal strategy of the role player. Find the optimal strategy of the column player. So this kind of question is not about solving the linear programming problem, it's about just formulating the linear programming problem and then understanding that the optimal solution for the other player is just the solution to the dual problem. So you can use complementary statements to find the optimal solution for the dual. Okay, and well, so basically these are the standard kind of questions. In past exams, there were some years where such notation was used, and these things, well, these are what we call the security levels, the pure strategy security levels, well, tier 1 and tier 2. So these things from past exams just mean your strategy security levels, and just The reason it was called Scream is because if you cannot control yourself and you just scream your strategy before playing the game, then this is the outcome that you should expect. You call it your strategy security level. Okay, so as you see the material, well, there isn't kind of that much of material, and most of the types of the problems, most problems of the types that we either had in the homeworks or had in the midterms. Only about the kind of last part of the course we didn't have either homework or midterm, so we have to practice alone. Once again, if you want me to check some solutions, you can send them by email to me or put it on my door. Oh yes, for the homework, how to submit the homework, you just come to my office and either give it to me directly, or if I'm not there, just sleep it under the door. Okay, so maybe any questions about the names of the topics themselves, any kind of questions? Okay. So I promised to one of the students to discuss such kind of thing, parametric linear programming question. I've taken one from the past final. The question was, so it's 2009 final, question number 7. Maximize the function which is 4x1 plus 5x2. Subject x1 plus x2 smaller than k. x1 plus 2x2 smaller than a. And 2x1 plus x2 is also smaller than b. x1 positive, x2 positive. So that's the problem. The question is like this dictionary. X2 is 3 plus x3 minus x4. x5 is 1 plus 3x3 minus x4 is the final dictionary for k, which is equal to 5. So given a problem, it has a parameter in it. x3, x4, x5 are just the names of the variables, the select variables for these three constraints. And you are given the last dictionary for one particular value of parameter, k equal to 5. The questions are, first of all, so first question, find the corresponding dictionary for any k. So we have the dictionary for one value of k. We want to find the same dictionary but for any kind of k, any value of k. So this question is not about the optimal dictionary for any value of k. This is just about the corresponding one, the one where the same variables are basic. Yes, yes, something like this. So we should treat this as basically a problem, well, either in sensitivity analysis, you are given one problem, and now you are changing one of the coefficients from 5 to k, or as I said, revised simplex algorithm. You know what basis you're looking for, and just use the formulas to update. Given this problem, you know what is the basis, and try to update. Okay, so for, let's say for the revised simplex algorithm, we need to know, well, first of all, what are the basic variables. That's easy. x1, x2, x5. They're just written over there. More important is B inverse. What is the value of the inverse of the basis matrix? Of course, it's not hard to find B. You formulate this thing as a dictionary. You'll just look at the first column as a table. You'll look at the first column, second column, and fifth column. But there is a better way to find B inverse. So what is it?
It comes from the coefficients of x, 3x, 4x, 5, and the dictionary.
Yes, exactly. So we know that this dictionary is the optimal dictionary when k is equal to 5. Let me write down the same dictionary in the form of table, because it's kind of more familiar for us. We dealt more with tables than with dictionaries. So let me write this table as, so x1 plus 2x3 minus x4 is equal to 2. x2 minus x3 plus x4 is equal to 3. x5 minus 3x3 plus x4 is equal to 1. And z is 23 minus 3x3 minus x4. So that's our table. And we know that B inverse is just right here. It's the coefficients of the select variables. 2, minus 1, 0, minus 1, 1, 0, minus 3, 1, 1. So we know what B inverse is. And now the only question is, we are making an update to the right hand side in the original problem. The original B was 588. Our new revised B is 888. So the revised right hand side, instead of being 231, will be the inverse times the revised value of B on the right hand sides. So it will be 2 minus 1, 0, minus 1, 1, 0, minus 0, 1, 1, 8, 8, 8. And let's see, it's 2k minus 8, minus 8, but minus k plus 8, so 8 minus k, and minus 3k plus 8, plus 8, so it's 16 minus 3k. So implicit in what I'm doing here is the understanding of how the change in the right hand side propagates to the final dictionary. I know that there will be a change only in the vector of the right hand side, not in the coefficients in the objective function, not in the matrix, only here. And then I know that the final, but rather the corresponding table for the updated vector of right hand sides is the same thing as it used to be here. 1, 0, 2 minus 1, 0, 0, 1 minus 0, 0, 0 minus 3, 1, 1, z minus something minus 3 minus 1. Now let's figure out what stands here, here, and here. So here we have 2k minus 8, 8 minus k, 16 minus 3k. The value of the objective function, well, it does change. We have different values for the variables. We should expect a different value for the objective function. So how should we find this number?
Just plug it into the original.
Yes, plug into the origin. I know my z is 4x1 plus 5x2. So this thing will be 4x1 plus 5x2. In other words, it's z minus 8k minus 8. Sorry. 8 minus 2, so 3k, and minus 32 plus 40 plus 8, so minus 8. Alright, so that's my new corresponding table. So maybe any questions about this first part?
We don't have to solve for k when this is feasible.
So this question just asked the corresponding table. The next part will be find z star as a function of k for any positive k. So find the actual optimal answer for any positive value of k. So that's part B. That's optimal. And now, well, now we will have to understand when this dictionary, when this table is actually the optimal table. Well, it is always optimal, so when it is a feasible table. And then if it's not feasible, do something about it. Update it so it will become feasible. So first of all, in what range just this table is feasible? So the table above is feasible and optimal when all these numbers on the right are positive. That's the only thing that we want. So 2k minus 8 is positive, 8 minus 8 is positive, 16 minus 3k is positive. We don't care about the value of the objective function. The objective function will be whatever it wants to be. Just these three inequalities. And let's combine them. I.e. So first one tells me k is at least 4. Second one tells me k is at most 8. This one tells me k is at most 16 over 3. 16 over 3 is just a little bit more than 5. So I have k between 4 and 16 over 3. So these options do not cover the whole range. They only cover the range of keys from 4 to slightly more than 5. 5 and 1 third. We still have to cover the range from 0 to 4 and from 16 over 3 to infinity. So let's do it step by step. For k is smaller than 4. We have this table. I'll have to copy it once again. So suppose that k is smaller than 4. We should think about k being just slightly smaller than 4 because, well, we want to make a change which is pushes only several of these numbers, a small amount of these numbers to being negative as possible. Then we'll make update. We'll find a new table. Then we'll see when this new table is feasible, in what range when k is smaller than 4 and maybe greater than something, this new table will be feasible, and then we'll see what to do next. Okay, so when k is just slightly smaller than 4, this number is negative. These numbers are still positive. So I'll have to make an update using, of course, the dual simplex method, because my solution is optimal, but it isn't feasible. So I choose the most negative row, the most negative coefficient on the right. It is this one, it's the only negative one here. Then I choose the smallest positive quotient here. Once again, there is only one option for me. This quotient is 1. This quotient is negative, so I don't care about it. And I make an update using the revised simplex algorithm. So have, okay, so let's see. I want just to check that these numbers are positive, so let me just first write down the expressions for these numbers, and maybe that's enough for us. So we have such a table. In the first row, I just multiply by -1, so I get 8 minus 2k. In the second row, I will add 1 times the first row, so it will be 2k minus 8 plus 8 and minus k. So just k. In the third row, I add 1 times the first row, so it will be 16 minus 8, 8, plus 2k and minus 3k, minus k. In the objective function, I will have to subtract the first row, so it will be z minus 3k and minus another 2k, minus 5k, minus 8 and minus another minus 8, so just minus 5k. These coefficients, well, if I chose the correct pivot row and pivot column, they should be negative. So just to be sure, let me actually perform this. I mean, strictly speaking, I don't have to complete anything right now. But just to be sure that I didn't make a mistake, I remembered how to perform the dual simplex algorithm correctly. Let me make that big. So 0, 0. Over there, it should be -5, minus 90. So it's still optimal. I chose, quite likely I chose the correct column to make that big. Some coefficients here, doesn't really matter what coefficients. What does matter is this number is positive, k is smaller than 4. This number, well, it might be positive or negative, depending on whether k is positive or negative. Luckily for us, we are only required to deal with the case when k is positive. So this is greater than 0. This is greater than 0 for k positive. So in the range for k between 0 and 4, the objective function is justified. If I did have to investigate what happens for k negative, I would, well, still write the same thing and then say when k is negative, and then perform a new iteration of the right symbol sum. Alright, so now we covered the ranges from 0 to 4, from 4 to 16/3, still one range left. Oh, could be several sub-ranges, but one larger range is left, from 16/3 to infinity. So for k which is larger than 16/3, once again, let me copy this dictionary. Notice that I don't want to deal with this dictionary. I updated it, but this only worked when k was smaller than 4. It should not work on the other side, So I want to update the original dictionary over here. 0, 1, minus 1, 0, 8 minus k, 0, 0, minus 3, 1, 1, 16 minus 3k. Minus 3 minus 1, z minus 3k minus 8. So, if k is slightly smaller than 16/3, what happens? This number becomes negative, all the other numbers stay still positive. So, this row will be my pivot row for the revised simplex algorithm, because once again, only this number is negative. The positive quotients over here, here the quotient is 1, here it is negative. So once again, you have only one choice for the pivot column. And then you make that update. Once again, just in the beginning, just compute whether what we get is feasible. So in the first row, we have to take this, multiply by 2/3, and add to the first row. So times 2/3, so the case cancel out, and I get 16/3. 16 times 2/3 minus 8. 8/3. Over here I get, I'll have to add, so to subtract 1/3 of this thing. So minus k minus k, so it's 0. 8 minus 16/3, which is also 8/3. Here I have to divide by minus 3. So I get k minus 16/3. And for the objective function, I just take the last row and subtract the third row. So it's z minus 3k minus 3k and minus 8 minus 16, so minus 24. So this new dictionary is feasible. These two numbers are just always positive, they don't depend on k at all, and this is positive for k which is at least 16/3. So once again, we are quite lucky, we don't have to make any other iterations. So for k which is at least 16/3, let's start with k is 24.
Yeah, is it guaranteed that there'll always be finitely ranges to analyze?
Yes, just because, I mean, each range corresponds to a certain choice of basic variables. So each dictionary corresponds to some variables being basic. And there are only finite many choices how many variables could, how many choices are there to make some variables basic. There are only finite many variables, finite many choices on n variables out of the set of all variables. So yes, it will be always finite many. So, and as we said, we'll always get something which is, if that data is on the right hand side, we'll always get some continuous function which is piecewise linear and which is concave down. So in this case, let's sketch the graph of the star of k. When k is from 0 to 4 is 5k. So it reaches 20. When k is from 4 to 16 over 3, it is 3k plus 8. So when k is 4, it's 3 times 4 plus 8, 12 plus 8, 20. And goes from 20 to 16 over 3 times 3, 16 plus 8, 24. The slope is 3, so it's smaller slope than this one. And finally, when k is at least 16 over 3, it's always 24, horizontal line. So we do see a piecewise linear function which is concave down. So it's not that we can be sure that our answer is correct, but at least we get some kind of stamp of approval like this continuous function which is concave down, it's reasonable. So maybe any questions about this? Any questions in general? So I didn't prepare any other questions and nobody asked me any other questions, so we'll stop right here. So thank you very much. And we'll end the time.